Hey guys, welcome back to video 2 in advanced optimization. And today we're going to be plotting 3 additional portfolios. The first is going to be a portfolio based on a momentum strategy in which we're going to be long the best performing industries from the previous year and then short the worst performing industries from the year prior. We'll then calculate the market portfolio, which like the momentum portfolio is unoptimized. And then the final portfolio we're going to build is the tangency portfolio. And then we'll just wrap up with some analysis and data visualization as always. Let's get started with the momentum portfolio by going inside our first portfolio design loop to take the means of the 47 industries based on the ith year in the sample period. And we're going to do that using the apply function as always. And we're going to also do the same thing for variance. So we can just copy this formula down, change the variable name, and then instead of taking the mean, we'll take the variance. And it's important to remember that these variables just store the values for the mean and the variance of each of the 47 industries for the year from 1992 to 2017. We now have the necessary information to calculate optimal weights for our momentum portfolio. So we're going to leave the portfolio design loop because it's an unoptimized portfolio and assign the variable WM subsetting from the first row to the number of years in our sample period. And this is essentially just storing our portfolio weights for each year based on the prior sample year. And then we're going to set this equal to a rank function where 50% of the weight will be put on the 4 best performing industries and negative 25% weight on the 4 worst performing industries. And 200% in the best and negative 100% in the worst industries equals a fully invested portfolio. So once we have the weights for the momentum portfolio, we just need to multiply it by our returns to get the portfolio performance as always. So I've gone ahead and done that already because we did that for the 2 global minimum variance portfolios. The only thing you need to do is manipulate the portfolio return variable to add another column so we can therefore put the momentum returns within this portfolio return matrix. And I've gone ahead and plotted the momentum portfolio, and you can see over the 25-year sample period, they had an extremely high return, but there was a very high variance to accompany this high return. But this is pretty reasonable since we're only invested in 8 assets for this momentum portfolio. But we really don't know on a risk-adjusted basis whether the global minimum variance portfolios outperform the momentum portfolio. So I've gone ahead and drawn a straight line from the point of origin to the momentum portfolio based on its Sharpe ratio. And you can see the 2 global minimum variance portfolios have a higher Sharpe ratio and therefore risk-adjusted return. And it's again leads us to the low volatility puzzle. And this can be further shown if we just do a quick calculation, Newport divided by standard deviation to get our Sharpe ratios. And you can see that the highest Sharpe ratio was, again, our first minimum variance portfolio. And on a risk-adjusted basis, our momentum portfolio did the worst over our 25-year sample period. Next, we're going to plot the market portfolio as well as the tangency portfolio. We're now going to calculate the tangency portfolio by using expected returns that are proportional to our vector of betas. So we're going to set the variable WWW equal to the inverse of the covariance matrix multiplied by our vector of betas. And then to calculate the optimal weights, we're just going to subset from the ith iteration of the sample period minus 1991. So you start at the first row, and we're going to set that equal to WWW divided by the sum of that to standardize it. Before we plot the tangency portfolio, let's go ahead and calculate the market portfolio because it should be easy as it's a non-optimized portfolio. So we'll set the variable RMRF, so it's the return on the market minus the risk-free rate, is equal to our returns variable, and then we're going to subset from our year, which is greater than 1992, starting with our 1993 investment period, and we're going to set this equal to our number of industries plus 2, as that's the column of the excess return on the market from our sample data. So to calculate the mean, we just need to annualize it, so we'll set this variable MUMKT is equal to the mean of RMRF times 252 to annualize this number. And then just to calculate the standard deviation, it's the same thing. Standard deviation in the market is equal to SD of RMRF times the square root of N, or the square root of 252. Gone ahead and plotted the tangency in the market portfolio, and you can see that of all the optimized and unoptimized portfolios, the global minimum variance portfolio with no index-based covariance matrices was the best performing over our sample period. So this is the end of this video, but in the next set of videos, we're going to look to implement beta constraints to our portfolios and really seeing if a higher beta indicates a higher return because of the higher risk associated with it. I hope to see you there.